We're building a telemetry engine for fully autonomous robots, sending telemetry data. However, because this is something that can be built over a weekend, because all the telemetry data needs is ability to read and write. That's it. But things get interesting at massive scale. We require the system to handle 1 million requests per second of sustained traffic and 32 kilobyte payload in each request. So by design, we will be handling 32 gigabytes per second of data transfer and storing 82 petabytes per month. We also require reading capabilities, live read, and access to the stored data by time range. Handling 1 million requests per second today is not a challenge. It's a thing that is done in the past. However, things get complicated when we want to remain within fiscal parameters. We cannot afford at this time operational costs that are beyond our capital allocation. We first approached this design by the industry standard. However, leveraging a traditional database like PostgreSQL will fail because independently it will force hardware to organize itself, which as a result will immediately degrade write throughput. The industry standard is to introduce a Redis cluster as an in-memory buffer. Redis ingests payload directly to RAM, which significantly increases ingestion rate to an acceptable level. A background worker is introduced to slowly drain that RAM buffer to the persistent storage. This design will fail in 30 seconds because the drain rate is slower than ingestion rate, which eventually will fill up the Redis in-memory buffer to its capacity. As a result, system will block incoming telemetry data and make permanent data loss. Because traditional choices cannot be leveraged, we transition to cloud-native managed services. These services are strategically selected. However, we are hit with a few bottlenecks that are inevitable in AWS infrastructure. Despite we achieve any design or select any service, these blockers cannot be eliminated. 1. Network. The egress cost, which is a byte that goes out from infrastructure to the internet, we pay 4.2 million for 84 petabyte of data transfer. That is for the live dashboard read alone. Second, the S3 cost, which is 1.7 million, which multiplies each month. Despite we achieve the best design in the world, we cannot remain under the fiscal parameters and reduce operational costs to what we can expect and within our capital allocation. To resolve this issue, we must move away from AWS infrastructure. We transitioned to OCI, Oracle Cloud Infrastructure, for a number of reasons. For the inbound traffic, for a byte that comes into the infrastructure is free. There are no costs. And outbound traffic is highly cost optimized and costs less than half if compared to AWS infrastructure. Third, the S3 cost is also less than half, making OCI infrastructure a strategic choice for our goal. In this design, we are operating with a Golang API fleet because we have competent Golang engineers available. It operates with C++ C-star ecosystem, specifically Red Panda Broker, Dragonfly, and ScyllaDB. By replacing traditional choices like Redis and Kafka, we bypass kernel friction and achieve true mechanical sympathy. In essence, these technologies reduce operating system overhead, and thus we increase throughput. And in this design, the Golang API fleet is appending data to Redpanda Broker, which is rewrite of Apache Kafka. Redpanda operates with a append-only system. It is appending data and it is not organizing the data. As a result, we get RAM-like speed on a disk. However, reading from Redpanda Broker will introduce a massive latency headwind. Consequently, Golang API concurrently writes to Dragonfly cluster for high-velocity reads and live dashboard access. Now we need access to historical data. A background worker, it slowly drains the Redpanda broker to a persistent storage ScyllaDB, which organizes data in an efficient way. This architecture technically scales, but it fails the fiscal parameters because we are over-provisioning each layer. Redpanda operates with Raft consensus quorum, which means for a high availability system, we must replicate the cluster into at least number of 3, into the multiplication of 3. This is a limitation because of Raft consensus quorum. It gives us highly available system, but we lose fiscal parameter requirement. Despite how complex this design is, it is merely a buffer because ScyllaDB is operating with a local NVMe. So when a node fills up to its capacity, we must provision a new node. Third, we significantly increase our exposure window. Because ScyllaDB is operating with local NVMe, despite a replication factor of 2, we have massive data exposure window. Because if a node goes down, we lose permanent data with it because data relies on local NVMe. In this design, we reduce the same architecture to bare minimum. Now, Golang API operates with ScyllaDB directly. However, ScyllaDB operates with a LSM tree. It has compaction, index updates. Because ScyllaDB has these requirements, operating with a network disk will introduce in massive over-provisioning requirement in the network pipe because each byte is going out to the network for management. So in essence, for ScyllaDB, we're looking for the multiplication of the required disk speed to well over 4 times. We require a design, we require a technology that requires less disk speed so that we can leverage network disk. We are leveraging network disk because they are cost optimized and they're highly available. We have technology named Aerospike DB. Aerospike operates with similar to Redpanda in a append-only system, and it has index in the RAM. For Aerospike, when a read query comes in, it consults with the index that is in the RAM and takes the data instantly. It is a 2-hop system. We get instantly faster reading system and write system. Aerospike seems to resolve all the problems until we realize that it also requires management of the data. It is managing data in a way so that the index can pull the data instantly. At the end of the day, Aerospike is a not free technology, unlike any other technology that we just discussed. Leveraging Aerospike DB requires enterprise license, and that is not one-time fee. It depends on how much data we are storing. 84 petabytes is 1 month of data, and that data is multiplying each month. Not that we are only paying for storage, we are also paying for license cost. At this point, we have tried multiple architecture designs, and each of the architecture that we had made leverages off-the-shelf technology. The technologies we have tried so far are some of them achieve true mechanical sympathy, like Aerospike database and ScyllaDB. They bypass kernel friction and increase throughput. Despite achieving the best results from the technology, we could not remain within fiscal parameters. To resolve these problems and remain within fiscal parameters, we must move away from off-the-shelf technologies and develop our own solution, introducing state machine ring buffer architecture. In this design, we are ingesting traffic from load balancer and appending data to Elastic Network Disk. What Elastic means, we will discuss that shortly. We are not leveraging any off-the-shelf technology here, like ScalarDB, AeroSpike. We are offloading data from network disk to OCI object storage. For reading from OCI object storage, we will use OCI Big Data Service, which will provide us ephemeral VMs to read from OCI object storage at fast speed. We are operating with cell-based architecture. How we configure cell-based architecture to achieve 1 million, we will discuss that shortly. But in this diagram, we are showing you one cell. And in each cell, we are handling 250,000 requests per second. And each cell has 12 VMs. Each VM has 40 OCPU and 128 gigabyte RAM and 50 GB boot volume. These are the specifications that we have done strategically to achieve our goal. Because OCI commensurately allocates network speed gigabytes per second to the number of OCPUs, and 40 gigabytes per second in a VM is the peak. It is the limit. We cannot go after that. We cannot increase network speed after that. 128 gigabytes RAM give us room for the buffer, operating system, and the application. 50 gigabytes does not store anything other than operating system and software. Each VM has attached 8 network disks. Each disk is configured with 1.5 terabyte, 120 VPU. 120 VPU is the maximum limit of VPU that we can assign to a network disk. And to get the full disk throughput, we also need to increase the capacity. We cannot get the same throughput for small capacity. To get the maximum disk speed we can get from a network volume, 1.5 terabyte is a holy grail number. In this design, we have 3 full domains. Initially we preferred 4 full domains. 3 full domains still work for us. So this is the system that how it works from this infrastructure level, how it works from within the VM. We're ingesting data from network load balancer to RAM and appending data to active network disk. There are 2 network disks that we are operating with at one time, at the same time, simultaneously. After ingesting data and appending data to an active network disk, after it gets full, we freeze that disk and we continue writing to the next disk in the order. A background worker slowly drains the frozen disk that was full to OCI object storage. For live read capability to power live Grafana dashboard, we are getting, after the data is coming in from network load balancer to RAM buffer, we are directly reading from RAM buffer. We don't need to consult with network disk or frozen disk or OCI object storage. We're simply reading from RAM buffer. And for reading the historical data, we're operating with OCI Big Data Service. This is how we achieve all of our goals from the architecture level. This diagram is the core of the architecture. It explains how we eliminate the buffer issue in previous iterations. The most common issue that we had in the previous iterations is that we were experiencing data lag, data gravity at the compute level, that over time, eventually those buffers fill up to their capacity, and as a result, a systemic failure occurred. Now, in this architecture, we are operating with state machine network disk. Now, to explain this, let's take 3 disks out of 8 disks. Let's name them A, B, C. So when the data is coming in from ingestion, we turn on disk A and append data to it. And after the time it gets full, we freeze that disk and operate disk B. We are offloading data from disk A while we are also ingesting data to disk B. And over time, when disk A is empty and disk B gets full, we cleared the disk A for reusing it, and by that, we're operating with 2 disks in a cycle. Now, disk C is a backup buffer. So by the time disk B gets full and disk A is not offloaded yet, we use disk C as a backup buffer. It is possible that OCI object storage can get slow. Disk C is used as a backup buffer. And by like that, we use disk D, disk E, disk F as a backup buffer. By the time OCI object storage catches up, we move back to disk A and disk B cycle. Now, it is possible that we use all number of disks, 8 network disks, we use all of them. We also have configured emergency provision on-demand disks so that when all disks are used up, we provision new disk using OCI API and terminate them by the time OCI object storage catches up. To understand how this architecture resolves the issue of data lag and data gravity issue that we had in previous architectures, this is how. We have 4 cells, and each cell we have 12 VMs. And by math, we are ingesting data. We are ingesting and handling data in each node for 680 megabytes per second. The data is ingested at 680 megabytes to a network disk. We're also reading 680 megabytes for live read, and we're outbounding that data to OCI object storage. We are also reading data, not at the full speed, we leave some headroom. The important thing to note in this architecture is that VMs that are listed on OCI infrastructure, they have full duplex advertised network speed, which means that we can ingress for 40 gigabytes per second and also egress 40 gigabytes per second, which means we get 80 gigabytes per second of total network capacity. So this is the math here. We are ingesting 680 megabytes from load balancer. We are reading from the frozen disk at 2 gigabytes per second. That makes total reading load 2.68 gigabytes per second. And the VM gives us 5,000 megabytes per second. That's 40 Gbps that we get in the VM. We have tremendous headroom here. This is the data that is leaving the VM. We are writing data to the active disk. We are serving data from that RAM buffer, and we're uploading data to OCI object storage that makes total 3.3 gigabytes per second. And we have 5,000 for that. We have comfortable headroom here. This is how the Golang application is programmed. We're operating with a React system and leveraging mmap. So we are ingesting data from network load balancer. And from the GNAT, we're following a reactor marriage pattern. We pin each CPU core to a sub-reactor, and main reactor is assigning data, assigning connections from network load balancer and intercepting. This design prevents context switching by keeping core in its own zone. So we're operating with sync pool and atomic and integer 64. This way we can map 100 GB file directly into RAM as a joint file array. So in essence, when payload arrives, CPU does one thing, that is increment the offset by the payload size. The network request is handed the exact slice that belongs to it. No other request can touch those bytes. Achieving this way, the CPUs can operate at full maximum efficiency without worrying about mutex contention. And then we have mmap, which is taking physical file from block volume into the Golang memory. This way, Golang can write to that, and then the operating system flushes down to the block volume. This function, copy, is as close to the hardware as possible a high-level language Golang can get. In essence, so at the end, we're shifting bytes, not transforming, not serializing. We're simply shifting bytes. This is a reality. Because of this parallel nature, we will not have ordered data in the chunk. It can be like 1 minute to 5 minutes, then 10 minutes to 15 minutes. It will not be linear one-to-one. This is why we need B-tree index that operates in the RAM. This is not limited. This only takes the data of a chunk. It does not take all 84 petabytes index. It only takes the index of what is going to be in the chunk, and then it clears itself. And yes, B-tree does bring up some complexity and some overhead to this architecture, but at the end of the day, we require B-tree to make data, to increase data integrity. This is important, otherwise we will land on wrong timestamps. And that's not the only problem here. At the end of the day, because compute nodes are stateless, if TCP creates problem, if drop packets create problem, and all of these, if they create problem, B-tree is the only way we can save ourselves. So when we are offloading data to OCI object storage, we leverage this B-tree as well by creating a complex path. This path contains the date, time, everything necessary using this B-tree. So by the time 100 GB chunk is uploaded to the OCI object storage, we execute madvise to clear up the memory space, the virtual memory space. We have OCI Big Data Trino service. This is separate from this architecture. When it reads data, it is consulting directly with OCI object storage. It does not do anything to the VM compute nodes. For the live client active, as mentioned in previously, it operates with a global toggler. So when an administrator is opening a Grafana dashboard, this global toggler turns on and it yields the gRPC or WebSocket connection to the client for powering up the live dashboard. This way, we achieve live data read and have access to historical data, and we are writing with data integrity powered by B-tree index. The true brilliance of this architecture is that this is shared networking architecture, which means that each node is an atomic unit of scale. Now, and previously I said we're operating with 4 cells, this is because we wanted to divide our call with 250,000 requests per second. This is redundant. We don't need that. We only did this to reduce operational overhead and understand the system more easily. And LC object storage is a elastic service. It can ingest data as fast as the architecture can allow it. We are outbounding data from network disk to OCI object storage at the speed of 2 gigabytes per second. This way, we are achieving fast drainage rate than ingestion rate. So because this architecture operates with a atomic unit of scale, because each VM is a separate and independent, we can increase how much the system can handle by simply adding one new node into the system. That's how brilliant it is. No garbage collection spike, no log contention, no disk thrashing, all of that achieved today, it will be same tomorrow. Despite the system operates with network disks, which are highly available, if a network disk does go down, it is only 1.5 terabyte. At the end of the day, if it goes down, we're only losing 3 minutes of data. And this system is also resilient to, if a node goes down, these disks will remain. But they will be an orphaned stage. When a new node comes into the place, this node must read these data to construct B-tree index. By the time these orphaned network disks get offloaded to OCI object storage, we terminate the new VM that we just provisioned and continue the architecture like it was before. This way, the architecture continues to be more and more reliable. We're leveraging OCI API to do all this. Now, at the end of the day, not any architecture is all green. We understand that reality. This architecture does have some problems. These aren't the problems that we have discovered so far. The maintenance trap, because we offloaded the complexity from off-the-shelf technology to custom storage engine, then maintenance trap has been increased significantly. Because we have Golang competent engineers, we can accept the trade-off. But in reality, this system, the software, is complex. Only the Golang engineer that has understanding to how Linux works, how the mmap works, how the B tree works, how to leverage them fully at their capacity. What is the reason that we achieved this design? All of this must be understood correctly in order to maintain this, which will create some friction in the onboarding engineer side. Second flaw is OCI API. OCI APIs can at times take some time to provision new nodes on demand. While we achieve pretty good utilization rate and the system has good ability to heal when disasters occur, we still have to consider that when the time comes, these OCI APIs cannot be reliable. For that, we have configured the system so that when a system is used, when a VM, to be specific, is using 60% of the available network disk, we in advance leverage these OCI APIs with retry system. This node death and data recovery problem is what we discovered previously. When a node goes down, it leaves these orphaned network disk, and they have dirty data that is not offloaded to the OCI object storage. The only complexity here is to construct a B tree from the available data. So as a backup, as a reliable system, we keep a backup of B tree into the disk at the same time. This is related to the maintenance trap, the split brain write map we are achieving with state machine. We have to reliably leverage each disk correctly. The hidden financial tax is related to the large number of OCI API calls for putting data from network disk to OCI object storage. Now, we already discussed that we will be doing 100 GB chunks. That is the reason with 100 GB chunks, we reduce the number of calls and achieve operational costs that are within fiscal parameters. But speaking of fiscal parameters, we have achieved massive undertaking of 1 million requests per second with 32 kilobyte payload under 150,000 infrastructure cost. That is significantly low if compared to other iterations that we have gone through. Only the cost that is a true bottleneck here is the storage cost. OCI Object Storage is the only service that can give us cost optimized storage. There are no other cost optimized services that can give us charges lower than that. This is the main cost as of today. And now the problem with the storage is that it will scale over time. And by the time we scale from 1 million to say 5 million, 10 million, 15 million, this architecture can still aid us. The infrastructure and compute part is completely fine. The only bottleneck here is that how we are storing the data. Storing data is achieved by offset. So each data is completely done without any compression. As of today, we're constantly getting data from this architecture to understand what are the things that we can improve. The main bottleneck here is the features that we can have access from the Golang programming language. For the future, when we scale to 5 million to 10 million, we will leverage compression system and trim system, where if the telemetry data is having identical data from 1 minute to 10 minutes, we will trim that data to one record. But that will introduce in a massive index system. And we are also replacing Golang storage engine to Intel DevKit libraries. Most importantly, the Deos, PDK, and DPDK. By leveraging these technologies, we also leverage RDMA for network by transferring data between nodes at lightning speed. This architecture is for the future. We will leverage this architecture. We will execute this architecture after we scale from 1 million to 10 million. It was a long journey. We went through many iterations of the design to get to this point. We removed off-the-shelf technologies and leveraged a custom storage engine to achieve our goals. At the end of this architecture, we have achieved slow ingestion rate and fast drainage rate. This way, the system does not have data gravity or data lag. The center of gravity goes out to the OC object storage, and this way we achieve data equilibrium, and no data goes anywhere stuck. This way, we achieved our goals reliably. Thank you for going through this journey. My name is Abdullah Memon, Principal Architect, Memon Systems.